All right. So this is the recording on September 8th, 2025 for our upcoming discussion on September 9th on Tuesday during the usual class hour. So I'm pre-recording this and will post this afternoon for you so that you would be able to go through this and maybe ask me a question if you would understand something in this discussion. So I will simply discuss a few problems. They are solved in diatoms. Maybe we'll provide a little bit more details over here. And I will do this discussion just based on my lecture notes. And I will start with the spherical pendulum. And after this, I will also consider a two-body problem. I will record two videos so that it will be just kind of, split into chunks, and you would be able to consider them in a separation. All right, so let's start with the spherical pendulum. So I mentioned that we have just a usual pendulum, but now we will consider three dimensions. Okay, so as before, with just a usual pendulum, we would have a constraint, and the constraint is because of the length of the string, right, from where it is fixed to the location of the mass. So this length is supposed to be L, right? So it will be fixed by L. It all is in presence of the gravity force shown over here, and we want to describe the motion of the spherical pendulum. And you will see that there will be some new interesting differences compared to what we encountered before in just the usual pendulum. Okay, we are going to introduce spherical coordinates as written over here, and this will resolve immediately the constraint that we have. And therefore, if I work with these new coordinates phi and theta, I would not need to write any, not to perform any of this Lagrange multiplier complication, right? So, okay, so in these new coordinates, I'm going to compute the velocity by taking the derivative with respect to time. Now, obviously, phi and theta are time dependent, so I have to take the derivative with respect to those variables here. And then construct essentially the kinetic term. Okay, so the potential term is pretty simple for my choice of the coordinates. It will be given by minus mgz, okay, and therefore the potential will be given by this combination. Okay, so now we have the degrees of freedom. We have theta, we have phi. In this case, phi dot square enters into the kinetic term, and we also have a theta dot square. So we can immediately notice that there is no dependence on phi in this Lagrangian. So the Lagrangian is phi independent. It only depends on the velocity phi dot. And therefore phi, as we learned last time, is a cyclic coordinate or ignorable. And we can write the corresponding conservation law. Okay, so the corresponding conservation law would tell us that the quantity J given by dl d phi dot, or this is nothing else but just this combination, if you take the derivative of the Lagrangian with respect to phi dot. And this combination is a constant. And I will call this combination J, right? So I will call this combination J. So let's call this equation number 1. We will refer to this equation as we move along. Okay, so now we can also write down the equation of motion for theta dot. This is pretty straightforward. We're just writing the usual Euler Lagrange equation, okay, over here, and the Euler Lagrange equation so equals 0. So we just substitute dl d theta dot, take derivative of this with respect to dt, and we will substitute dl d theta and put everything into this equation. We will get something like this. I mean, what terms are present here? Well, the second derivative with respect to time of theta. There is also phi dot. squared present? Well, that one is appeared when we were differentiating this sine of theta. And what else is here? Well, there is also this combination again, so this is just from the potential term. So now we see that this is a pretty complex equation. It has phi dot squared, it has theta, double dots. So how we can simplify it? We can actually substitute equation number 1, okay, or express in equation number 1, we can express phi dot, okay, in terms of this constant j, and divide by the sine square and other coefficients. And this is exactly what I've done here, but instead I just actually wrote phi dot times sine square theta equals to this combination. Anyway, so after this you can just solve for phi dot and substitute it back into the equation of motion. And once you've done this, you are going to simplify this equation. So this is the resulting equation. You will simplify it now to just express theta dot now minus something. Okay, so this equation, theta dot minus something, I will rewrite in this form over here. Okay, and this form tells me that theta dot plus some derivative of some effective, the derivative of some effective potential. Okay, so this combination I will just denote by the derivative of this effective potential with respect to d theta equals to 0. Right, so this is just by analogy with what we did before. Right, so this will be the force, right? So this with negative sign, when you put it on the right hand side, will be just the force, right? So just by analogy of what the force is, we can write this as some effective potential, and we will analyze it now. Moving on. So one important note here is the following: you should not try to substitute the equation 1 into the Lagrangian, okay, ever. Okay, you shouldn't try to substitute this into the Lagrangian. So you cannot do it. First, you have to vary with respect to the variables, so in this case theta. With respect to the variables, in this case it's just theta, you have to vary it, and only after that you can use the conservation laws. Okay, and it's regardless of what conservation laws we are talking here about. It's energy conservation, and it is in this case conservation of angular momentum. Okay, it's regardless of that, you cannot substitute those conservation laws into the Lagrangian. You can only eliminate things on the level of the equations of motion. So in the equations of motion, we could use, and we did use, this conservation law, and we substituted it into the equation itself, not to the Lagrangian. Okay, anyway, we obtained this combination over here with this effective potential. And next we're going to analyze it. So this analysis is essentially is known by the name of effective potential approach, quote unquote. Okay, so from this definition we can just find what the effective potential is by integrating with respect to theta. This will be this function which we can actually sketch. Okay, this is effective potential as a function of the theta. So the second term will give me a negative cosine, so shown over here, and the positive term, so this contribution will give me a 1 over sine square theta. So at small thetas, the sine square will go to 0, and this term is going to blow up. It will go to infinity, and indeed if you sketch it, so it will be like this. Okay, so at any non-zero j, at any non-zero j, okay, at any non-zero j, and by any means the j will be defined by the initial conditions, yes. At any non-zero j, we will have the potential barrier. Okay, so we will central barrier, right? So we will have a central barrier where theta goes to 0. There will be infinity in the potential. While if j is non-zero, then the barrier disappears and we obtain this type of potential. This already tells us about possible solutions. For example, if our initial conditions for the energy will be, well, in this case for this effective potential will be within this range, right? So then our motion will be constrained between these 2 points. Yeah, and these points will define as the points where where we have the turning position for our trajectory. But we will talk about this a little bit later. Okay, so now, we can actually go ahead and solve this equation, but instead we can also recognize. So if we go back to our calculation, we can also recognize so that it will conserve the energy, okay, or analog of energy. So and the analog of energy here is given by this combination. So again, so just by analogy, you probably remember that we derived the conservation laws for the harmonic oscillator. In that case, it was, and for many other things as a matter of fact. So by analogy, we can, from this equation, we can construct the conserved quantity, and you can actually check by taking the derivative of this conserved quantity that it is indeed conserved. You just can take the derivatives and you will see that if you substitute the equations of motions, once you take the derivative of this quantity, it will give you 0. All right. So from here I can find theta dot squared. It will be 2 times E minus V effective as a function of theta, and after this we can take the square root and finally integrate with respect to time. So while we're taking the square root, so let's consider this combination over here. You can see that if my initial conditions at 0 velocity were given somewhere over here, right, the initial conditions, so the initial energy was given, this is, we'll call E here, the same E as in this point. Then the positions when my effective potential crosses this line at the given E will define me the positions at which my velocity turns to 0. Okay, velocity becomes 0. And the velocity becomes 0 only to change sign after that. So you will have a positive velocity, it crosses 0, and then it becomes negative. And this is why these points are called the turning points, because velocity flips the sign. So next, we can formally integrate this equation, right? It's already, we have full separation of the variables. So we will have the variables which depend on theta only on their left-hand side. We will form this integral afterwards, and everything which depends on time will go to the right-hand side. In this case, the time dependence is really trivial, just linear time dependence. So we can formally integrate this equation. So in this case, it will be pretty complex because V of theta is a very complicated structure, a complicated function, okay, given over here, and that one would be not as easy to find the integral of. But formally, this is solvable, right? So we can formally integrate, obtain theta as a function of time, okay. And if we wish, once we obtain theta, we can go ahead and use the equation 1 to then obtain phi, right? So phi is going to be given. So written over here, phi is going to be given the integral of 1 over sine of theta of t. But you remember from this equation we already find theta. We can just substitute over here and be done with this problem. I'm not doing this explicitly again only because the integrals are going to be pretty ugly. But the main idea is like this. So the main novelty here compared to the usual pendulum is that we now have the central barrier for the initial conditions when we have non-zero angular momentum, so non-zero value of this parameter j. Alright, now I see you in the next problem.